In this video, we'll begin Chapter 4, which is a discussion of blocking, so a statistical concept called a block, and the randomized complete block design. So again, this is going to be Chapter 4 in your textbook. We're going to be talking about this concept of blocking, and actually what this is related to is a concept that we call nuisance factors. So we'll be discussing that too. When we implement blocks in our design, this really is kind of like combining our ANOVA and accounting for a nuisance factor at the same time. And when we tie those two in, we tie in our randomized complete design with the block, we get the randomized complete block design, or the RCBD, and you'll see this acronym relatively common, and you'll hear this design. It's a very common, well known, and often used design. So again, this is an extension of the ANOVA, and we're going to have to consider how we're going to change our analysis method to account for this new type of design. So we're going to learn about this extension of the ANOVA, which is going to let us analyze this type of design. And then we're going to have to look at some other issues that come out of this, but also learn how to account for some other factors. So here we say nuisance factors. Randomized complete block design can account for a single nuisance factor. What happens when you want to account for two nuisance factors or three nuisance factors? The designs do become somewhat more complicated. And I think what you're going to see here is, again, what we've been saying kind of through the whole course. That is that this is a course about design. So the really interesting thing about the randomized complete block design is not really the analysis. The analysis is going to feel very underwhelming, and as well it should, because this isn't about that analysis. The cool part that we're going to talk about is the design, and that's going to be our big takeaway. So before we even get into there, we really have to talk about what are blocks. So what are these blocks that we're talking about statistically? So blocking is how we deal with these nuisance factors. So what is a nuisance factor? Well, nuisance factors are just factors that affect the response, but that we don't care about. So if it affects the response and I don't care about it, then by definition it's a nuisance factor. The variability, however, is a problem with these, because if we don't account for this, it's going to make the response vary. And if so long story short, if you recall back to our signal versus noise, the TV signal versus the white noise, if we just leave in the nuisance factor, it's going to add to the white noise. So what we want to do is remove the nuisance factor from the white noise so that we can look more closely at the signal that we care about, the TV program we're trying to look at. So that's what the idea is going to be, is that we want to statistically and through our design account for nuisance factors such that we reduce the amount of white noise that we have. So again, these nuisance factors, we know that they add to the white noise, but again, it's not something interesting. So it's not like a second TV program that I want to study. It's just something completely random. Now, there's a whole bunch of different kinds of nuisance factors you can have. So our textbook uses these kinds of things: batches of raw materials. We have different individuals who are operating the machinery, different types of machinery, etc. But very often one of the most common blocks is actually this idea of the individual and the operator. So what we commonly block by is we say, okay, well, if Susie's going to be running these three tests and Tommy's going to be running those three tests, then we want to account for the fact that Susie's running these, Tommy's running those. So accounting for individual is a very, very common type of nuisance factor that we want to account for, because usually I don't really care the difference between Susie and Tommy. I'm just trying to study the underlying thing that they're doing, and I just need to account for the fact that they are both different. So many social and industrial experiments use this or should, and what I mean by this is like This always, I shouldn't say always, very, very often happens. And again, if you think back to that individual case, very often we have individuals who are doing multiple tasks within something, or we're doing all the tasks maybe split over 2 days, so we need to account for which day it happened. Or maybe we're taking all of our samples from a particular location or batch, or maybe these locations or batches are split out, and we need to account for that too. Again, there's so many different ways that we could include blocking factors that it tends to be a really good idea to do so. And frankly, it just tends to appear all the time, which is why we may want to do so. Maybe a last note here is that failure to include this type of factor, this blocking factor, is something that's pretty common. And that's why I mention up here or should, because very often we don't account for blocking factors. Think about an experiment where I'm looking at the number of replications in something like exercise, and I don't account for the factor of types of exercise I'm doing. Now, I might not care about what type of exercise I'm doing. I might be studying something else, like how many exercises can I do when it's hot out or when it's cold out or something like that. But maybe I need to account for the fact, well, different exercises are going to have different amounts that I can do. So this is something that is an important consideration, but again, is commonly not included. So what's the consequence? What's the consequence if you don't do blocking and you really should have? Well, we actually talked about that right at the beginning. The blocking factor and all of its variability gets added to the white noise, so that when you're studying that white noise, or when you're trying to study your TV signal, the white noise in the signal is a lot stronger, or some degree stronger. However strong the blocking factor is, some degree stronger. So we would prefer if we could make that a lot weaker, the white noise, if we could tune that down so that we could better see the TV signal of the TV show we're trying to watch. So that's the idea here, and that's the consequence. The consequence of not including this is that it gets included in that random error. Now, not all nuisance factors are things that we can control via blocking. So sometimes we have nuisance factors that are not controllable via blocking, and in that case, we're going to have to take a slightly different approach. But for nuisance factors that are controllable via blocking, what we have to do is they have to be both known, so we have to know which factors they are, and we have to have the same amount of control that we do over our independent variable. This is not quite true, but this is largely true. At some level, we do have to be able to control it. The exception we'll talk about in a bit is like when we have natural experiments, so where it's not really controllable, but we can take advantage of what's naturally happening. All right, so if the nuisance factor is known and uncontrollable, sometimes we use the analysis of covariance. So this is a nuisance factor, uncontrollable. So typically it's a number, sometimes typically it's numeric, continuous, sometimes it's categorical, and then we use the analysis of covariance to account for that covariate, that uncontrollable nuisance factor. But if it's known and controllable, typically we use blocking. Now, if it's unknown, how do we account for variables that are unknown? So we can't control it because we don't even know it's there. Typically, the unknown variables are called lurking variables, and we've already talked about this. We talked about this near the beginning of the class, that we hope that the randomization, not random order, though random order helps us to make sure there's not an order effect, which would be a known and maybe uncontrollable factor. But the random order helps us to take care of that. The randomization, what we're talking about here, is a random assignment of the experimental units to the groups. That is what balances out the impact of unknown and uncontrollable variables across the study. So again, these are going to add to white noise, and that randomization doesn't help reduce the white noise for unknown and uncontrollable variables. What it does do is it helps to make sure that these don't have an impact on the validity of our results, that is, our interpretation. Said another way, if these were there and we weren't using randomization, our interpretation couldn't necessarily be causal because it could have been caused by one of these lurking variables. So that's where we have to do correlational statements, and that's why we like experimental design, where we do have random assignment and have necessary, though not necessarily sufficient, cause to make causal claims. Now, sometimes several sources of variability get combined into a block, so the block kind of becomes an aggregate variable. And all I'm saying here is that blocks, let's think about, I've got different kinds of metal that I'm testing or something. Maybe the thing like thickness of metal and type of metal and particular construction and all these different aspects are really included when I say I'm blocking by this single sheet of metal versus this other sheet of metal versus this other sheet of metal. There's a lot of things that could differentiate these sheets. And if I block by the whole sheet, then I'm kind of combining all of those into a single block. Don't think too hard on this. Just realize that sometimes if you can use a large, clearly defined variable, even if it has some other things that kind of make it up, that works just fine. So the rule of thumb here, block what you can, randomize what you can't. All in all, it tends to be better to account for the white noise. Because remember, when we randomize, that doesn't reduce the white noise. That just helps make sure that the TV program we're tuned into isn't actually a different TV program. That's what a lurking variable could do. But it doesn't reduce the white noise. So randomization is good in that it makes sure our TV program's what we're trying to actually watch, but it doesn't reduce the white noise. Blocking reduces the white noise, and so that's a nice thing to reduce that TV static. So when we can, we want to make sure that these nuisance variables are blocked out, because now it's known, it's taken care of, and because it's taken care of, we're sure we're watching the right TV program. Also, because it's taken care of, the white noise is reduced. But if you can't block stuff out, and sometimes, I mean, it's not just that you don't know the variable. Sometimes it's that it is just really inefficient or really costly to block things out sometimes. And if that's the case, then you randomize what you can't block out. So block what you can doesn't mean like sell your farm and your house and your firstborn child to block every variable possible. It means block what you reasonably can or should, maybe the big ones or a big nuisance variable, and then randomize the rest. And why do you want to randomize the rest? It's so that you make sure you're tuned into that correct TV program and that there's not these lurking variables that are impacting your analysis. So block what you can, randomize what you can't. All right, so in those previous, we were talking about blocking as kind of adding on to something, so as a new component. But what happens if you're like considering between, well, should I block a variable or should I include it as an independent variable? And actually, blocking is not just another independent variable, and we'll talk about that. Blocking is actually restriction on randomization. But the previous slides, again, we talked about blocking versus doing nothing. So what if we're trying to decide between blocking and an extra independent variable? So we're going to talk about three common thoughts here, or I guess the third one we'll kind of address subtly. So two common thoughts here, I should say. But one is, if we care, it should be an independent variable, and if we don't care about it, it should be a block. That's kind of what we've been thinking thus far. So for variables that I care about, independent variable I don't care about, it's a nuisance factor, we call them, a variable that's there but doesn't really matter to me, then I block it out. A second common thought is if I'm adding the variable and it's only got one replication, then that variable's a block. And so this is another thought that's not necessarily true. Both of these are decent rules of thumb. The problem is, and again, I say both of these are rules of thumb. Actually, both of these have come out of like a website or a textbook where they say this is how you tell the difference between an independent variable and a block. And I should be clear, for an introductory course, either of these is probably fine. You see that these are very different than one another, that like one doesn't exclude the other, but it's not entirely inclusive of the other either. They're kind of a different thought and a different thing that we're looking at. This one's looking at replicants. This is looking at the design of the experiment. Do you care or not care? So for an introductory course, these are probably fine, but I want to go, because this is a a major course, go a little bit deeper into the distinctions between these and talk about why reality is just a bit more complicated than just saying, I care, so it's an independent variable, I don't care, so it's a block, or because I only have one replication, it must be a block. It's not quite that easy. So let's dive into it, and we'll talk about the first one. So the first one, block isn't just an independent variable that you don't care about. So this is a really, 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 really important statement. Do whatever you have to do. I have a highlighter here. Let's see if I can highlight it. Hopefully you guys can see this. Highlight, bold, whatever you've got to do. This is really important. Blocking represents a restriction on randomization. Blocking represents a restriction on randomization. Blocking represents a restriction on randomization. An extra independent variable with an extra IV, I would just take my experimental units and just split them into the different levels of each IV. With blocking, though, typically blocking represents a restriction on randomization. So whether it does naturally or not, blocking is something that I can't necessarily just randomize through, or in my design, I don't just randomize through both independent variables. So it's important to realize the big difference between a blocking factor and just an extra independent variable is this design change. Now, why is this so important? This is so important because the analysis is going to be identical. The difference is the design. The design actually changes because we do our randomization in a different way for a blocking factor. So let's look at what I mean here. Let's say an experiment is we're doing laser etching on cutting coupons. These are just little bits of metal from a big ingot. And then we're going to repeat the process for several ingots. So you've got this big block of metal, and I'm just slicing off little pieces of it to do an experiment with. But after I finish slicing all the pieces, I need some more pieces, so I get another big block of metal, and then another big block of metal. So though I could and then I want to do some laser etching on the little slices. So though I could randomly assign each little slice to a laser, if I pick up a slice, I can't randomly assign that slice of metal to which ingot of metal it came from, right? If I pick up a piece of metal, that is already assigned. I can't pick up a piece of metal and randomly say, oh, this came from the first block or the second block or the third block of metal. And I should say ingot instead of block because the statistical concept is a block. So I'm going to say ingot, and when I say ingot, I just mean a block of metal. So I can't pick up a little chunk of metal called a coupon and randomly assign it to an ingot. That doesn't make any sense. If I pick up a chunk of metal, it came from one of the ingots. I know it came. I can tell which one it came from, perhaps, if I recorded that. But I can't randomly assign it. So that second, the variable of ingot, is one that I may want to account for because, hey, these ingots might have been made differently, subtle changes in the metal, et cetera, et cetera. But it's not one that I can randomize. So this is a known variable, but I'm restricted on randomizing this because of the design. The design says I need to chop up all these different slices of metal. But again, I can't pick up a slice of metal, which is my experimental unit, and assign it to an ingot. How does that differ from the independent variable? So ingot would be a block because it represents a restriction on randomization. I can't randomly assign to an ingot. How is it different than the laser? Well, I could pick up a piece of metal and say, well, I'm going to stick this in laser 1 or laser 2 or laser 3. So if I pick up a little chunk of metal, I can randomly assign it to laser. So laser could be an independent variable. But even if I cared about ingot, it doesn't matter how much I care about that variable, I can't randomly assign it. I can't randomly assign the experimental unit to that particular ingot. And this is where a block isn't just an extra independent variable that you don't care about. An extra independent variable that you don't care about, I could randomly assign the experimental unit to. So let's say the person operating the laser is something. Well, I could randomly assign this to a different person operating the laser. Now there's some potential issues with that, but I could, for the purposes of this current example, I could randomly assign this slice of metal to person 1, laser number 4, or person number 3, laser number 2, right? I could randomly assign this to that. But for blocking, I can't necessarily do that. There is a restriction on the randomization, so I consider that a blocking factor. And again, this is so important to realize at the design level because that's where this changes. This changes at the design level. This changes at the experiment level because it changes how you run the experiment. Again, I can't randomly assign the little slice of metal to an ingot. So my experiment has to take that into account, that I can't randomly assign this to both of the variables. I have to randomly assign this to the independent variable I care about, and then I have to somehow account for the block in the design, and we'll talk about that later. So it changes the design, it changes the implementation, and it also changes the interpretation at the end of how we can interpret blocking. And in fact, what we'll find out, not in this chapter, but in the next chapter, is this will also change the analysis slightly. It represents not only a restriction on randomization, but also a restriction on analysis. All right, so the second issue that we can have is that sometimes we only have one observation within a combination of two independent variables. And though this isn't particularly common to happen within two independent variables, sometimes it does happen where we have two variables that we really care about, that we don't represent restrictions on randomization, and we have just a single replication that happens due to cost or time. So the kind of thing that we're speaking against here is sometimes you'll hear, oh, well, if you only have one observation, then the second variable must be a blocking variable. And again, that's not necessarily true. It's not necessarily false either. It could be if it represents a restriction on randomization. And it could be if we choose to have that happen. We'll talk about that next. But sometimes we do care about both variables, and we care about them in a way that we want to study both variables, and we want to include an analysis of both variables as independent variables. Again, we'll talk about how analysis is restricted later, but it can happen that sometimes with two independent variables, not one independent variable and one blocking variable, that we just have one observation within the combination. So real quick, let's say we consider the case where we're looking to make the most efficient cutting tool for cutting gold, right? And so we're looking at the shape and the material that it's made out of, but because of how expensive creating a gold plate to be cut is, we may only use a single replication. Even though it's not like either of these variables represent a true restriction on randomization, nor are either of these variables nuisance variables that we just want to account for. Both of these are variables that are important for us as part of our study, so we want to make sure we're including those and addressing them as such. So this would be a great example where due to cost constraints, we only have a single replication within two independent variables. And I tell you what, we'll stop this lecture here for today. For the next one, we'll pick up with the next consideration, which is that sometimes we do have a choice as to how we treat these variables.